Hello, everyone, and thank you for coming. I'm Vinayak Gupta, and this talk is about learning neural models for continuous time sequences with missing events. And this is a joint talk between IIT Delhi, IIT Kharagpur, and IIT Bombay. So, time series are popular in many real world applications, such as social networks, healthcare, finance, and online shopping. And standard way to model a time series is via temporal point process. A TPP assumes that there's a sequence of events, and each event in a sequence has a discrete mark and a continuous time, and the time is always increasing. TPP also assumes that the future events are influenced by the past. So, for the sake of simplicity, you can assume that a TPP is like an RNN that can process continuous time. Now, the problem that we try to address is pretty generic. So, any purchase records of users of clothing and eating outlets and financial transactions can be represented as a sequence of events in continuous time. And existing models assume that each event in a sequence is observed. So the sequences are complete. This is highly ideal and rarely encountered in practice because you are bound to miss some events due to crawling restrictions and privacy restrictions. To overcome this situation, we propose IMTPP, an acronym for intermittently observed marked temporal point processes, which learns the dynamics of both observed and missing events simultaneously. It achieves this feat by using a coupled TPP framework, where each TPP represents one for observed events and one for missing events. So we model missing events as latent random variables, and we follow a very standard approach of incrementally updating the hidden state of the TPP whenever we see a new event. So before we go into the model, just take a look on the standard notations. So we consider a sequence of observed events and a sequence of missing events that is generated by our model. And since we model missing events as latent variables, we use observed TPP and two TPPs for one for missing event prior and one for missing event posterior. So the modeling procedure of IMTPP is pretty standard. So given two observed events, we use our model to sample the first missing events between them, and then we sample the next missing event, and then we repeatedly sample the missing events between these two events till we reach the next observed event. Now for the neural formulation of it. So as TPPs assume that each event in a sequence has a discrete mark and continuous time, our model should be able to embed both of these features. So we whenever we have to embed an event, we embed the time, the mark, as well as time interval of it. Using this event embedding, we update the hidden state vector of our observed TPP, and then we sample the mark of the next event, and then the time of the next event. Note that for sampling time, we use log normal distribution. This guarantees closed form sampling and a faster convergence. Now our TPP for observed events is actually, as you can see, is very much similar to the observed TPP. However, there's a very stark distinction that for sampling the mark and time of the next event, here we use a truncated log normal because since we are trying to generate missing events between two observed events, our last missing event should not exceed the time interval of the next observed event. Therefore, our sampling procedure has to be bounded. For simplicity purposes, I have excluded the diagram for prior TPP, but it follows a similar architecture. Now, how is our model trained? So, the likelihood of observed events demands marginalization with respect to the set of latent missing events. However, we don't have that. So, what do? We resort to maximizing the variation lower bound of the log likelihood, or you can say we maximize the elbow. Now, coming to the results. So since our goal is to predict the time as well as the mark of the future events, we first evaluate our model and the state-of-the-art baselines for observed event prediction. And we use a very two standard metrics. For evaluating time, we use a mean absolute error, and for evaluating the accuracy, we use a mark prediction accuracy. So a comparison on 6 datasets shows that our model is best in terms of time prediction and comparable for mark prediction. Then we also perform a qualitative assessment where we consider two individual sequences and we try to plot the actual inter-event time intervals and the ones predicted by our model. So as we can see here, that the difference between the two time series is not different, and uh, IMTPP can very well handle the generative procedure. Later, we also perform a very interesting experiment where we actually try to impute missing events between time series. So in the following figure, the sticks with blue are the observed events and the brown are the missing events. So we try to do a synthetic deletion where we remove a few events from the sequence and we try to predict it. So as you can clearly see, IMTPP can very well understand the dynamics of both missing and observed events. Now we also do a very interesting experiment on forecasting. That is, we try to predict the next k events in a sequence while giving only the current sequence as input. So we note that even for forecasting, IMTPP outperforms the state-of-the-art models by a lot. And in terms of scalability as well, since IMTPP, the underlying model of IMTPP is pretty standard and pretty simple. So we note that the other state-of-the-art model that actually handles missing events takes around 24 hours when you train a sequence of that 100, where IMTPP on the other hand takes around 5 to 5.5 hours on the main datasets. Now to conclude, existing time series model assumes that data is complete, which is ideal and very rare setting. And we propose IMTPP, which is a method for incorporating missing events and for training mark time point processes. Experiments on very large data sets show that our model can outperform all the standard baselines for mark and time prediction. And the best notion is that including missing events improves over standard learning procedures. Now, this paper appeared in AISTATS 2021. A reviewer gave our work a rating of 10 on 10 and labeled it groundbreaking. For more details, you can please scan this QR code for code implementation as well. These are the references of it, and thank you and stay safe.